So
very
just wait,
happy.
hold on one second, Ethan. It's still trying. Yes, now it's okay.
Okay.
Go ahead.
So we're very happy to have Damiano Testa from the University of Warwick today, who will speak on contact in algebraic and tropical geometry. So Damiano, please.
Yeah, so thank you very much for inviting me and for the introduction. I normally would have liked to be present there, but I guess this will have to do given the overall situation. So I hope you can all hear me and you can see the slides clearly. I really welcome a lot of interaction. So online it might be, I don't know if more or less worrying for people to interact, but please do interrupt me and ask questions. I prefer to spend more time explaining something that is unclear than to get to the end of everything that I prepared. So please do interact. All right, so I'm going to be talking about contact in algebraic and tropical geometry, and I'm not going to assume a lot of knowledge in tropical geometry, in fact, almost none. And I'll try to keep the knowledge of algebraic geometry also as low as possible, especially at the beginning. I'm imagining that there's lots of non-experts like myself in the audience. So let's see. Let's see what I have prepared. So I see now that the slides are a little bit big. Let me zoom out. And maybe, sorry, I didn't realize it was not in full screen. So let me try to find out full screen mode. Okay. All right, so this is the outline for the talk. I'm going to start with some overview and talking about background, trying to explain all the names that I will talk about later. In particular, I'll give examples of inflection points and bitangent lines of plane curves. Then I'm going to move on to elementary approaches for computing bitangent lines and inflection points. I'm going to then talk about specifically inflection points and inflection lines and highlight an important difference that appears between them. You might be used to thinking that inflection points and inflection lines carry the same amount of information for a curve. I'll try to highlight the fact that there's actually a subtlety there, and that's exactly what we're going to exploit. So I'll stress this once we get there, but it'll be a subtle but important distinction. Then I'll do briefly a similar kind of argument for bitangent lines, showing how the same methods that were applied for inflection points and inflection lines and the distinction between them can be applied to bitangent lines. And finally, I'm going to conclude with further directions. So this is a plan for the talk today. All right, so what is the goal? What is it that I'm going to talk about for bitangent lines and inflection lines? So in a lot of recent and not so recent algebraic geometry, people have tried to find maybe enumerative answers to questions for classical constructions that involve producing the number of rational curves in the plane, for instance, going through some fixed number of points, or counting bitangent lines to plane curves, or inflection lines, or lines on cubic surfaces. So there's lots of results in algebraic geometry that involve counting things. And a lot of these results have then been either reinterpreted or proven or reproven using tropical geometry. And tropical geometry is very helpful from this point of view because it gives more or less a recipe for converting a sort of very geometric, very sort of non-linear problem into something that has a tendency of being more linear or at least more combinatorial. And then counting the combinatorial types often yields interesting insight on the complex counts. And the interesting thing is that there's lots of very beautiful success stories relating this. So there's lots of cases where tropical geometry really allows you to get the same exact numbers you get in complex geometry. And there's lots of effort and results into proving that, in fact, you can use the tropical numbers to actually deduce that the complex numbers had to have been the same. But there's also certain situations where tropical geometry gives numbers that are not the ones that you get from complex geometry. And in those situations, the reason why this happens seems to be more mysterious. There's not a clear understanding of which problems are going to work well with tropical geometry and which problems are going to give you an answer that is actually different from complex geometry. So the goal of the talk today is to present 2 or 3 results that for which the complex counts and the tropical counts differ, and explain that the difference between these two can probably be justified by sort of doing a similar count in positive characteristic. So not leaving the realm of algebraic geometry, staying in algebraic geometry, but specializing the field from the complex numbers to a field of positive characteristic. So doing a similar count in tropical in positive characteristic happens to yield the same result as in tropical geometry. And I'm going to give you a few examples of when this is the case, and try to convince you that this is actually something that has the potential of happening more frequently than just these few examples that I'm talking about today. And before I continue, let me say that this all that I'm going to be talking about today, all the new part, are joint work with Marco Pacini, and all the wrong things that will happen in the slides are just privately made by myself. Okay, so let's begin with some of the conventions that I'm going to be using. So when I say curve throughout this talk, I'll usually mean a projective plane curve. I won't be talking about abstract curves or curves in not even curves in tree space. I'm just going to be talking about plane curves. And I'm going to be working over a field K. And I specifically do not want to make assumptions on the field K for the moment. In particular, I will definitely be interested in the case in which the field is of positive characteristic, and in fact in some sense of a resonating characteristic with the problem. So when you often hear, oh, we're looking at a double cover, so we're excluding characteristic 2, I'll be sort of taking the opposite point of view, and I say, oh, if I'm looking at a double cover, I will be looking at characteristic 2. The reason is that this is exactly where this resonating thing is exactly what, from sort of our point of view, justifies why the tropical counts differ from the tropical count, from the geometric count, from the sort of complex counts. Okay, so curves anyway are plane curves. We usually don't care about special curves, so we'll always be thinking about general curves. So I may say some things that are true for every plane curve. I may say some things that are true just for smooth curves. And I may say some things that are just true for general, not necessarily only smooth curves. But I will be a little vague about this. If you're confused about it, ask me. But the general rule will be, if I say curve, I probably mean a general curve in the fixed degree that we're working on. In terms of how much I allow my field to be algebraically closed or not, I don't particularly mind. You can choose your field to be algebraically closed. This will not really play a big role. I won't be talking about things for which the absence or presence of roots is actually important. So if you're comfortable working with an arbitrary field, feel free to do so. If you prefer to work with an algebraically closed field, that will not affect what I'm going to say. It won't make anything sort of particularly trivial or uninteresting unless it was already to begin with for you. And in particular, if you only want to have a finite list of characteristics to worry about, important characteristics to keep in mind are 0, 3, and 2. So you don't actually have to worry for my talk about characteristic 5. But I will tell you when I'm actually specifically working in positive characteristic and what the characteristic is when it comes to that. All right, so having taken this out of the way, let's see what the main characters for my talk are. So I'm going to be talking about inflection points. So let's see. So this slide presents inflection points. If you've never seen them before, it's unlikely that you're listening to a talk in algebraic geometry and have never seen an inflection point of a plane curve, but nevertheless, here it's an example. So you can see, I don't know if you can see, yeah, you can see my cursor. So this is the Fermat plane cubic with equation x cubed plus y cubed plus z cubed is equal to 0. And these two lines are presumably the line y is equal to -1, so y is equal to -1 and x is equal to -1, they are inflection lines. So the intersection multiplicity, so they meet the curve, in this case at just one point, and intersection multiplicity at that point is 3 by Bezout's theorem. And in the case of the Fermat cubic, we can actually write down all of the inflection points for this curve, and they are exactly the 9 points that you obtain by essentially using 0, 1s, and the third root of -1 as your coordinates and vary this in all possible ways. So that's a computation that you have probably done. If you haven't done it, you've probably done it now in your head if you're paying attention, and otherwise it's not a particularly hard or deep result. And you can already start seeing that this equation here precisely defines essentially mu3, so the group of third roots of unity. And so you can already see that this is not going to be particularly concerned with what the characteristic is, unless the characteristic is exactly 3. And the sort of behavior that you see for this equation, that modulo 3 has a triple root, whereas modulo any other prime, it has 3 simple roots, it's exactly the kind of behavior that we're going to see over and over in this talk. So in some sense, this is sort of the source of everything that's going to happen. And this is, sorry, it's not the source, this is a consequence of everything that's going to happen. And we're trying to look for patterns that look exactly like this in a couple of problems. Okay, I'm just gonna make a small pause to see if there's any question. Right, so then let me change slides. So similarly, besides inflection lines, plane curves have other very special lines that people have studied for a long time, and those are bitangent lines. So here you can see an example of a plane quartic. For plane cubics, it doesn't really, there aren't really interesting bitangent lines to plane cubics. So a bitangent line, as the name suggests, is a line that is tangent to our curve at 2 distinct points. Remember that I mentioned that curves are general for me, so I won't be particularly interested in the degenerate case where the 2 tangent points are not distinct but happen to be the same. So for the purpose of this talk, a bitangent line could really be a bitangent line, not a quadritangent line at one point. Of course, you can extend it to that case, but it's not going to add much to what I'm going to say. So a bitangent line looks exactly like this. And in terms of coordinates, you can write down the equation for, say, this quartic in this way. And it's always going to be like this. It's going to be the square of a quadratic form corresponding to the 2 roots along the bitangent line, and then leftover stuff that is divisible by the equation of the line that you're using. And again, you see that you see a square of some polynomial here. And again, you can imagine the characteristic 2 will interact weirdly with the square, and every characteristic other than 2 will not interact with this, or at least will interact with this in the same way that any other characteristic other than 2. So this is, again, another one of these resonating things that happens. Characteristic 2 is a little special for this problem, and we'll see how to make this more precise. All right, so these are the main characters that will play a role in the future. So if there's any question about inflection points or bitangent lines, now might be a good time to ask. Okay, so let's continue. So here are 2 examples of what I was talking about before. So I know there's lots of beautiful success stories of tropical geometry counting exactly the complex solutions and giving the right answer for how many lines or plane curves or geometric configurations there are satisfying certain geometric constraints. But I want to specifically talk about the few outliers for this philosophy. And so here's a theorem, which I stated in a way, so I wanted to highlight the differences. So it's really 2 pairs of theorem that I've stated in this slide. So you either always take the root above, or you always take the root below in each theorem. So the first theorem states that either a plane curve over C of degree d has 3d times d minus 2 inflection points. And you would imagine that tropical d, I mean, why not? It may have the same number of inflection points, or maybe it has a different number of inflection points. And it turns out that a tropical plane curve of degree d always has d times d minus 2, not 3 times d minus 2 inflection points. So we see a sort of difference of dividing by 3 the number of inflection points when we go from complex numbers to tropical geometry. And another classical fact is that a tropical plane quartic over C has 28 bitangent lines. That's also something that, I guess, after the 27 lines on a cubic surface, probably 28 is the second most common number among algebraic geometers. And so 28 is the number of bitangent lines for plane quartic over the complex numbers. And if you do a tropical count, you actually only find 7 bitangent lines. As always, I'm talking about general curves, so you can find fewer if you want, but you should expect to find 7. But definitely not more than 7. And again, you can see that the difference between these two numbers, or the ratio between these two numbers, is 4. Here it was 3, and in both cases, it's a number that seems to have a relationship with the geometric configuration that we're talking about. Here we're talking about inflection points where the tangent line is multiplicity 3, and 3 is the ratio of these two numbers. And we were talking about bitangent lines, so lines that are tangent at 2 points, so multiplicity 2 at 2 points, and the ratio between these two numbers is 4. So I'm going to basically try to convince you that the intersection multiplicity shows up as a ratio between the numbers of the things you count. I'm going to do this in a couple of examples, and hopefully this applies more generally. Okay. Any questions about the slide? So this is presenting what is that I'm going to be worrying about. I'm going to try to explain the differences between these numbers. All right, as much as you can explain math. Okay, so let's see what we can add to the previous slide. So the theorems have stayed, so the top path and the bottom path stay the same. I just introduced an extra middle path in the two theorems we had before. And now I'm going to start making specific assumptions about the characteristics of my field. So for the inflection points problem, I'm going to be looking at fields of characteristic 3. And I'm going to call the field of characteristic 3 a field of characteristic 3. I'm going to call it K3. And one of characteristic 2, I'm going to call it K2. And so you can see that if you actually count the number of inflection points that a plane curve of degree d has over a field of characteristic 3, you will find that it actually has d times d minus 2 inflection points, not 3 times d minus 2. So even the count in characteristic 3 differs from the count in characteristic 0 and matches the count in tropical geometry. And
Damiano, can I interrupt? There is a question in the chat. So Cesar Augusto Hilario Poma asks, what is the definition of an inflection point of a tropical curve?
So I was going to gloss over this because it's not going to play a huge role. But essentially, so you can talk about intersection multiplicities in tropical geometry. And if you are a little bit familiar with tropical geometry and the way it's usually drawn with amoebas, I won't give you the actual definition, but essentially, if the line shares a segment with the plane curve, with the tropical plane curve, then that line is an inflection line. Now, if you're careful about, or if you know a little bit about tropical geometry, you realize that this means that if it shares a segment, you can move the intersection point along that line, and still it's going to be a tropical line with the same property. So you really shouldn't be thinking about specific inflection lines, but connected components of the set of inflection lines. So there's a notion of multiplicity that you can define that involves doing some sort of deform to a situation where the actual intersection number is computed by a determinant. But if you actually are in a situation where you have to do that for inflection lines, you actually already are as a line word, which is an inflection line.
So that it just means stable intersection multiplicity 3. That's what it means?
That's exactly what it means, yes. In terms of amoebas, because I'm really only looking at intersection multiplicity 3, it almost, so except for maybe 1 or 2 configurations, it means that they share a segment. But otherwise, it's the correct definition is that the stable intersection multiplicity is at least 3, and then you take connected components of the set, because you sometimes are allowed to slide the sort of the weird point of the line along a part of a segment of the amoeba for the other curve. And so you want to count all of these infinitely many inflection lines as corresponding to really the same. Keep in mind that from this point of view, tropical geometry, I'm viewing it as the limit of complex geometry. So I know to begin with that my problem only has finitely many limits because it comes from a finite problem in characteristic 0. So I know that I may have infinitely many potential limit points, but I know I only will reach finitely many of them. And somehow the statement is that every connected component of the limit contributes one inflection line from a source. Or in fact, we'll see not one because there is a factor of 3, but we'll kind of get to this later on. But I see I received the thanks for the explanation, so I think I answered the question. Are there any more questions about this? All right, so you may start wondering though now that what I wrote in this slide is a little bit funny because while when you define tropical things, multiplicities become a little bit of a pain, and it's not so easy to define multiplicities tropically. But when you're thinking about algebraic geometry, multiplicities are really the heart of every argument, and one of the main uses of thinking about schemes instead of varieties is exactly that you can do the generation arguments and compute multiplicities when you specialize and deduce multiplicities before you specialize, or at least global multiplicities. So the fact that the numbers change and decrease when you go from characteristic 0 to characteristic 3 or characteristic 2, you should be suspicious that there's lots of multiplicities involved in this. And multiplicities are exactly what's going to be the justification for why the complex numbers and the number of characteristic 3 are different here. Of course, the numbers counted with multiplicities must be the same. But the actual statement is that the numbers always carry multiplicities. So that's where I'm headed. That's what I'm trying to get at. The numbers of distinct solutions is smaller, but of course the number of solutions counted with multiplicity stays the same. The family is flat, and you do find the same number of points in the limit. Okay, but I wanted to state it like this to highlight the similarity with tropical geometry. All right, so also because it's literally correct, although it might be misleading and confusing if you are used to seeing multiplicities being preserved. All right, so let me continue. Okay, so here is the tropical side of how people have explained or argued or used inflection points in the tropical world, and tried to justify or did justify why you have this factor of 3. And so the argument in that case that you can find in work of Klein, Gronga, Shu, Viro, Brugalet, Lopez de Medrano is that the factor of 3 between the number of inflection points and the number of tropical inflection points can be justified by observing that a plane curve over the real numbers actually also has this number of inflection lines, which is divided by 3 from the complex one. And the upper bound is achieved. In this case, I said there's always a genericity assumption in the background that I'm sort of glossing over. So you can have fewer, they can collide with one another. You can have strange behavior where you actually miss some more. But basically, the takeaway from this perspective is that the tropical plane curve is trying to count the real points. And the real points are divided by 3 because with every real solution, there's another 2 complex conjugate solutions that are not real and cannot be real, but that add to the count of the total number of points. So of course, the total number must be 3d times d minus 2. And you still have 3d times d minus 2 distinct solutions to the system. It just happens that 1/3 of these are real, and the remaining 2/3 are in complex conjugate pairs, making up for what's left. Okay? So it's different from what I'm talking about, because here I'm working over a non-closed field, so I'm not guaranteed to find all the solutions that I expect there to be there. And indeed, I only find 1/3 of the ones that I expect to be. Whereas our fields of positive characteristic, we will be working with algebraically closed field, or we can be working with algebraically closed field. So we're guaranteed to have the same number of points, but the multiplicities will be distributed differently. So that's really the heart of the matter for us. Okay. One thing that you deduce from these results is that they're very elaborate, they're very refined and very sophisticated. And it takes actually a lot of effort to prove this. It's a very, very specific result. It gives a lot of information, and it carries a lot of extra implications with it, and it's hard. Whereas the kind of results that I want to talk about, they're easy to get at. They're not hard. They're sort of try to be as elementary as possible. And of course, we don't recover these results. We don't know that the set of solutions, or sort of we don't get any information on how the Galois group over the reals act on a set of points. But we get an information about numbers of curves and the visibility, specifically. Okay. So let me continue. Of course, as always, please interrupt me and ask questions if you have them. Okay, so here is the beginning of the elementary approach that we would like to propose. So as I said, we're going to specialize to the characteristic that sort of to the black sheep of the characteristics that people usually try to shun away. Whenever you see a paper that starts "let K be a field of characteristic different from something," my first immediate reaction is, well, I'm going to actually choose that characteristic and I'm going to try to see what happens. And this is what happens when you perform the strategy with the bitangent lines and inflection lines. So what we propose is we want to find a local approach going by a positive characteristic to justify why there are these differences. And the reason we wanted to do it like this is because we've seen that essentially the count is going to be skewed by the fact that multiplicities will change in positive characteristic or in resonating characteristic. And so it's really a matter of looking at the multiplicity of a single point once you specialize, a single inflection point or a point of bitangency, when you specialize from characteristic 0 to characteristic 3 or 2, depending on the case. And so the approach will be entirely local, and it will be local over a field where we can specialize from characteristic 0 to characteristic either 2 or 3. So I will leave the technicalities of mixed characteristic and everything, but you should really imagine that you have an equation over the integers and you're reducing it modulo 3 or modulo 2, and you're counting or seeing what happens in the reduction. So as I stressed now multiple times, we're trying to see how contact multiplicities interact with the characteristic of the field. And if a contact multiplicity is a power of 2 or a multiple at least of 2 or of 3, then characteristic 2 or 3 will play a special role for the problem. And so, for instance, for inflection lines, we'll think about characteristic 3, and for bitangent lines, we'll think about characteristic 2. And of course, these are just 2 examples, and I'll mention at the end of my talk a few examples where you see a similar behavior numerically. So where you have counts that have different answers in characteristic 0 and in positive characteristic, and possibly trying to justify them with the same methods. I know Israel is in the audience, and I've already seen the number 3,264 showing up. So at least it popped out in the chat at some point, and that will be the content of one of the last slides that I have. Okay, so here is the very basic computation that sort of around which everything that I'm going to be saying today hinges, and that really highlights a special property of when the field has positive characteristic relating to what are the multiplicities of the roots of a polynomial. So this and especially the next slide are the most technical slides of my talk. So you can either take the point of view that this is the moment where you want to pay more attention, or where you want to doze off, and after that it will be all be easier. So let's take K to be a field, any field, and we just take a polynomial in one variable with one root of multiplicity m. So we want to highlight or convince ourselves that the characteristic of the field and the multiplicity m, if the characteristic divides the multiplicity, then something else happens, something special happens, and we can kind of detect this. And we want to detect it geometrically. So what is the GCD between f and f prime? Well, if f has a root of multiplicity m, then you can write it like this. So I'm going to merge with the proof. And so when I compute the derivative f and its derivative, you imagine that this multiplicity m drops down by 1. You get an expression like this. So the derivative is divisible by m minus 1. The polynomial itself was divisible by m, so you certainly know that the polynomial will be divisible by x minus alpha to the m minus 1. No surprise here. What becomes, or might be a little surprising if you've never seen it before, is that actually you gain an extra divisibility in the case in which the characteristic divides m. Now, if you think about it, it's not that surprising, but it's something that, at least to me, was a little puzzling when I saw it the first time, and I really hadn't focused that this was really the main culprit for explaining these discrepancies. So let me show you how you do this, because it's very easy. So as I said, we write the polynomial as x minus alpha to the m times g. G is a polynomial, and we assume that g of alpha is non-zero because we're assuming that the multiplicity is n. So my definition of multiplicity is that this is exactly the order of vanishing of the thing. Notice that this is a sort of shorthand or sort of a formal way of saying that we're thinking about an inflection line if the multiplicity is 3, or we're thinking about a bitangent line if the multiplicity is 2, and there's 2 such roots. Okay, so we set up the problem like this. We compute the derivative. We get this expression here. So clearly, x minus alpha to the m minus 1 divides the derivative. And the statement that the GCD of f and f prime is divisible by x minus alpha to the m is just the statement that x minus alpha to the m divides f prime, because obviously it divides f by assumption. And so when does x minus alpha to the m divide f prime? Well, we've already written f prime like this, so it's already, the m minus 1 are already taken care of. So we just want x minus alpha to divide this part here. X minus alpha divides this, so it's just when x minus alpha divides m times g minus m times g. And we said that g is not divisible by x minus alpha, by our assumption. So m must be divisible by x minus alpha, which means that m is a constant, so it must be 0 in the field. And so this means that m is 0 in the field, and the characteristic divides m. Okay? So it's a very straightforward, easy argument. And it does show how the multiplicities resonate with the characteristic of the field. Okay? So in essence, I'm going to now transport this property to the case of inflection points and inflection lines of plane curves, and bitangent lines of plane curves. Any questions about this? All right, so let me make a comment. In the case in which the multiplicity is divisible by m, so in which we are in this weird outline case, the fact that x minus alpha to the m divides this really means, so recall m is divisible by the characteristic. So this factors, m factors as p times something else, and then x minus alpha to the p times something else is really x to the p minus alpha to the p times some, raised to some power. So the consequence of this is that whereas here I still have alpha as one of the coefficients of the expansion of this polynomial, when I expand this polynomial out and I look at the coefficients of this polynomial, the coefficient of x to the m minus 2 is alpha, or maybe m minus 1 times alpha. And so I actually have the rational function, so alpha is in the span of the coefficients here. Whereas here, we said the polynomial is x to the p minus alpha to the p raised to something else. So the most I can recover of alpha from the data of the GCD of f and f prime is something that is a pth power of alpha. Okay? So this is the basic inseparability property that I will be referring to later on. So in this polynomial, the coefficients at least suggest that I should have alpha appearing. So the function field of the solutions will involve alpha. Whereas here, the function field at best contains alpha to the p. And at best, it's contained in alpha to the p, and at best it is alpha to the p, but I am losing something. Okay? I will not recover everything. And this is exactly what's going to justify what we're going to say later on. So let me move on. The next slide might be even more inscrutable than this, but If I now merge what I said before and try to be a little bit more focused about it, I'm going to formulate this conclusion so if K is a field, P is a prime number, and then at least P is an integer. So there was, I'm going to make this assumption because otherwise what I'm going to say is not true. So then there is a rational function Rp of f0 fn in n+1 variables that has the following property. So the coefficients, the variables of this function are the coefficients of my polynomial. And basically, the function is going to express the fact that this polynomial has a root of multiplicity p. And so I'm going to formulate this by saying, so if the polynomial has a unique root of multiplicity alpha at least 2, and the multiplicity, assume that the polynomial has a unique root of multiplicity alpha or multiplicity at least 2, and assume that multiplicity is actually p. So in that case, I can write down a rational function of the coefficients that produces for me the coordinate alpha when the characteristic is not p. And when the characteristic is p, what I can do is I can write alpha to the p as a rational function of the coefficients. I'm not saying I cannot write alpha, but that was sort of implicit in what I said before. In the previous slide, let me slide back a little bit. I was saying that the best I can read off is x minus alpha to the p to something else. So I really do not have coordinates other than powers of p of alpha in the coefficients of my field. In the coefficients of my polynomial. And so here I'm saying, actually, I can write down alpha when the characteristic doesn't divide it. So in the good case, I actually have the variable. And in the bad case, I only have a purely inseparable extension of the ground field, of the field of k adjoint alpha. Okay. The proof is essentially an induction on the difference between n and p, and using the previous lemma. So basically, you compute the greatest common divisor of all the derivatives, in fact, the Hasse derivatives of the polynomial up to the p minus first, and you show that this GCD is either x minus alpha, and so or x to the p minus alpha to the p, depending on what the characteristic is, and then you basically play around with GCDs, and you know that the GCD of f and its derivative is in fact expressible as so the entries are expressible as rational functions of the coefficients of the polynomial. So basically, it's playing with Euclidean algorithm. Okay, so the main takeaway is that if you have the locus of polynomials that have a root of multiplicity alpha, that have a root of multiplicity p, and p is not the characteristic, then you have access to the root itself in terms of rational functions of the coefficients. But if the characteristic is p, then you do not have alpha you cannot reach alpha, but you can only reach alpha to p. Okay, so let's move away from this technical slide unless there's a question about it. All right, so now let's forget about this and
a silly question, but out of curiosity, what's the polar set of this rational function?
What do you mean by the polar set? Oh, you mean where the poles? Oh, I see. I haven't really thought about this. My guess is that if the multiplicity is higher than p, because the multiplicity at least p actually, so I think it'll probably be the case where the multiplicity is p squared.
It should be a hypersurface, right?
And I think it is because all multiplicities are multiples of p. So actually, multiplicity 1 higher automatically reaches for you. Sorry, maybe I said p squared. Maybe I should have said 2p. I have to think whether it's p squared or 2p. I don't know whether it's multiplicative or additive. But all multiplicities are actually at least p. And so if two branches come together, there's actually a p from one side and a p from the other.
Sorry, but the rational function isn't defined on the space of all polynomials? So I'm misunderstanding something.
Yeah, so it's a rational function of the coefficients of the polynomial. Yes, so it's on the space of all polynomials.
Okay, that's not important. It was just.
I'm glossing over the fact that, for instance, if a lot of the beginning coefficients are 0, that would also be in it. But I think the right answer is that if you have another root of multiplicity p, then that is the polar set.
Okay, thank you. It's not important.
But I may get back to, I mean, I won't do it during the talk, but I may amend what I said. I'm not sure. To be honest, we never really cared about this because we were always thinking about general curves. And in some sense, with a general curve, I precisely avoid these the poles of these GCDs. So I always put myself in this situation where all the multiplicities are P. Okay, so any further questions? All right, so what now happens in the case of inflection points? And here is where I'm going to really focus on the difference between inflection points and inflection lines. So you might be used to thinking that inflection points and inflection lines sort of determine each other. And now I want to highlight the fact that for the characteristic 3, this is not really the case. And there is information loss and gain into thinking about one and the other. And precisely the information you lose into going from one to the other is what allows you to prove the visibility results among the numbers. So let's go back to inflection points of plane curves. So we're going to fix a curve in P2, and we're going to look at the standard incidence correspondence of a point on the curve, and that is an inflection point, and the corresponding line, the corresponding inflection line on the curve. So X is my point in P2 that happens to be an inflection point of the curve, and L is the line that is tangent to C at X, and because X is an inflection point, it's an inflection line. As usual, I denote by the dual, the projected plane dual to L, so the space of lines in P2. And yeah, so then the question is, so basically, whenever you have an incidence correspondence, your first reaction should be, let me project on either side and deduce something that I cannot deduce about the other side by proving it for one of the two sides. And so in particular, I want to know whether projecting on the X coordinate or on the L coordinate gives me the same amount of information. So let's see what happens when we project on one or the other coordinate. So this is the setup. I just copied the same definition. And so now I'm going to go from inflection points to inflection lines, which means I'm going to fix my inflection point. So I'm going to fix my first coordinate. I'm imagining that I'm projecting onto the first coordinate. I have access to the coordinate X, and I want to see if I can reconstruct the coordinate L. So if I can reconstruct the tangent line to X, to the curve at the point. And of course I can. I just compute the tangent line to the curve at that point, and it's automatically the inflection line. And the inflection line is just computed by computing the derivative of the equation and evaluating it at the coordinates of X. And I have access to everything because the curve is fixed, so I have its equation. I have the coordinates X, so I can plug in the values of X0, X1, X2, the three projected coordinates of this, and I get out the equation of the line. So the equation of the line, so its coordinates. And so I can go from X to L without having to do any weird extension of my field. If I have the coordinates of X, I produce the coordinates of L. And they're just the derivatives of the equation of C evaluated at the variable of the coordinates of X. So this means that if I'm trying to count the number of points in the projection onto the X coordinates, so the number of inflection points of my curve, the number of inflection points of my curve is exactly equal to the number of points in the set, FC. And it's not just the number of points in the set, but it's really the number of points in the scheme. With multiplicities, I get the right answer, because I can literally reconstruct the coordinates of that. Okay? Not some powers of them, but literally the coordinates. So I really have that the scheme FC has as degree the number of inflection points of my curve C. The projection onto the first coordinate is an isomorphism onto its image. Very well. So this is how inflection points look like. So let's see what happens to inflection lines. Of course, now we're going to all expect something different. So what happens if I do the same argument, but now remembering the coordinates of my line L? So I'm going to fix my inflection line. I have the same set FC, and we're looking for a general line as usual. So our inflection line is going to be tangent just at X. Sorry, it's going to be a tangent line just at X, and besides being tangent, it actually has multiplicity exactly 3, because it's general and it's an inflection line. So it's not just tangent, it has a multiplicity 3. So if I look at the polynomial defining C, and I restrict it to L, I get, Well, the line is P1, and so this polynomial here is a polynomial in one variable that has a unique repeated root corresponding to the inflection line, and the multiplicity of this root is exactly 3. We're exactly in the situation of the space of polynomials that we talked about before. It's a polynomial that has exactly one repeated root, so at least one, exactly one root of multiplicity at least 2, and the multiplicity happens to be 3. Okay, and we already know that therefore characteristic 3 is now going to play a funny role. We're going to be able to reconstruct the root of our polynomial if the characteristic is not 3, but not if the characteristic is 3. So let me move on. So the setup is we fix that inflection line, C is general, we find this polynomial that has a multiple root of multiplicity exactly 3. And we've seen earlier, what can we say about reconstructing the root of our polynomial from the data that we have? If the characteristic is not 3, then we had that rational function of the coefficients of f that allowed us to write alpha as an element of the function field of the coordinates. And so I can actually write alpha specifically with that, evaluating that rational function at the coordinates of f, unless I'm in the polar set that Roger asked about. And so in this case, when the characteristic is not 3, I deduce that the size of my set is still also the size of the inflection lines. We didn't really gain much information from this trick of projecting on one coordinate and projecting on the other coordinate. When the characteristic of the field is 3, though, we saw that we can reconstruct alpha cubed. So we can reconstruct the cube of the coordinates, because we had that we could get x minus alpha to the multiplicity, and the multiplicity is 3, and the characteristic is 3. So we can reconstruct alpha cubed, but not better than that. So when we project fc onto the second coordinate, we're not getting a birational map. We're getting a map that is everywhere ramified of multiplicity 3, because every fiber is non-reduced, and every fiber has multiplicity 3. So this means that the size of the set that I see when I look at the projection onto that coordinate must be a third of the size of the set that I started with. And that's exactly where I get the divisibility by 3 on the set of inflection lines. Notice that if I didn't know the number of inflection lines of a plane curve, this argument is already enough to prove that 3d times d minus 2 is divisible by 3, even if I didn't know that the number was 3d times d minus 2. So we've actually shown that the number of inflection lines of a plane curve is divisible by 3 without having computed the number of inflection lines, or inflection points. I do not know what the size of this set is. I would have to do an extra computation to compute this number, and deduce that it's actually d times d minus 2. What I've shown now is just that it's divisible by 3. Okay, so let me continue. Are there any questions about this? All right, so then let's move on. So here is the summary of what happens in the diagram that I talked about. So here is the whole diagram. So I started with a set of pairs, the incidence correspondence of a line, of a point, of an inflection point and inflection line. The projection on the first coordinate is always birational, because I can always write down the coordinates of the tangent line from the coordinates of the point. When I project onto the other coordinate, I always get a purely inseparable map. Most of the times, it's purely inseparable and also inseparable, and it's a birational map. In fact, when the characteristic is not 3, that's exactly what it is. When the characteristic is 3, though, I do always get an inseparable map of degree 3, and the way to go between them is via the Gauss map here at the bottom. So the Gauss map is usually separable, and when it isn't separable, it's purely inseparable. So that's basically another point of view on this thing. We're just saying that the Gauss map is purely inseparable when restricted to the inflection points for a plane curve in characteristic 3. And the pure inseparability there is exactly what gives us the divisibility by 3 in the statements. So here I have an amusing consequence of this. So I said I would not really work with non-algebraically closed fields, or that nothing of this sort would play a role. But in case you happen to like imperfect fields, like I tend to do, So if you have a separably closed field of characteristic 3, so it has all the inseparability you want, but all the separable roots, and you take a general plane curve defined over this field, a consequence of this result is that the coordinates of the inflection lines are contained in K. So the inflection lines are defined over a separable extension of the ground field. And if your field is separately closed, they're already in the ground field. Whereas the coordinates of the inflection points are defined exactly in the first layer of applying the inverse of Frobenius. So you only need to extract 1/3 root of unity of possibly every element of the field. In fact, just of the coordinates of the line. So it's kind of amusing that you get some arithmetic consequence from these results. You don't have to go very far. You know that either they're in a separable closure or they're sort of one layer away from separable closure. Okay. Anyway, this was a very, very aside, just because I like fields of positive characteristic, and if you like them, then you like inseparable and imperfect extensions. Okay. So what happens for bitangent lines? Well, the story for bitangent lines runs entirely parallel, except that now we're thinking about, of course, now the characteristic that will be important is characteristic 2. And because we have a bitangent line, we're going to duplicate our arguments. Because our arguments were local anyway, we're going to argue separately on each one of the 2 points in multiplicity 2. So again, we set up the same incidence correspondence. We have a point on the plane that is a point of bitangency of our curve, and the line that is the bitangent line to the curve C at that point. And again, we play the same game. So we project once on the coordinate of one of the 2 bitangent points. This map is always birational because I'm still trying to recover the tangent line, and I can always recover the tangent line from the coordinates of the point. Compute derivatives and evaluate. On the other hand, when I project onto the second coordinate, so the coordinate of the line, I have now a root. So I have now a polynomial that has a double root. So the equation of the line and the restriction of C to the equation of C to the equation of the line gives me a polynomial that has a double root at one point, but I don't really have the coordinates of the root. I have the coordinates of the polynomial. And we've seen that in such a situation, if the characteristic is 2, I will not be able to get my hands on the coordinates of the root of the polynomial, but just of the square of that root. And so this highlights the fact that when the characteristic of the field is not 2, I have an actual double cover, because every bitangent line for a general curve is bitangent at 2 points, and those 2 points are sort of uniquely recovered by the coordinates of the line. Whereas when the characteristic is 2, I get a single purely inseparable extension of degree 4, because both of these roots I have to extract one inseparable root for one of the 2 roots, one of the 2 double roots of L, and another one for the other root of L. So this gives me a factor of 4 in the count for the number of these points that are equal to the number of bitangent points, but it's sort of 1/4 of the number of bitangent lines. And so here I summarize this, and so in particular you see that when the characteristic is 2, each contact point contributes 2 to each inseparable degree, and so bitangent lines so count with multiplicity 4 from this number here. And so notice that again we've proven that, for instance, the number of bitangent lines to a plane quartic over C is divisible by 4 without knowing that there were 28 to begin with. And in fact, we've shown that the number of bitangent lines to a plane curve of any degree is divisible by 4, without having to know the Plucker formulas or anything of the sort. Okay, so let me move on. So now the statements that we made about bitangent lines can be generalized very quickly to all the theta characteristics on curves of genus G. And in that case, the theta characteristics correspond to hyperplanes that are tangent at G minus 1 point to the canonical curve. So in that case, you imagine, you can see that there are G minus 1 point of multiplicity 2. And so imagine that there was going to be a factor of 2 to the G minus 1 between the complex count and the counting characteristic 2. And that's exactly what happens. So the complex count is 2 to the g minus 1 times 2 to the g minus 1 for the odd theta characteristic, and you just lose the factor 2 to the g minus 1 when you look at characteristic 2 count. You can also do a similar count for the even theta characteristics, but it's a little bit more involved because there's always a special theta characteristic in characteristic 2 that, in some sense, looks like it's messing up the computations, but it's actually making them work. Because this number here is not a power of 2. The total number of theta characteristics is a power of 2. So the other one has to be messed up somewhere. So it cannot be divisible by 2 to the g either, by 2 to the g minus 1. In fact, it isn't, but you can justify why it isn't. Notice that this is what happens in characteristic 2. We started wondering about how to justify things in tropical geometry. In tropical geometry, a similar question or analogous question to this is already open in genus 5. So this is not really well understood from the point of view of tropical geometry, but at least from the point of view of characteristic 2, it kind of seems that it should behave very uniformly. Okay, I see I'm a little bit running out of time, so let me just bring up this formula just because I saw Israel was in the audience. So there's another famous problem that deals with tangency of plane curves, which is the number of conics simultaneously tangent to 5 general plane conics. And this number is famously known to be 3,264 and all that over the complex numbers. This follows from work of many people. So the problem was proposed by Steiner, was solved by Chasles, then de Jonquière gave a general formula, and then Fulton and McPherson reinterpreted and generalized these more general formulas. A very, very cute result of Israel's is that actually you can do a computation in characteristic 2. We're looking at 5 plane conics tangent to a given conic. So we're imagining that there are 5 points of multiplicity 2. So we're expecting that 3,264 should be divisible by 2 to the 5th, given what I said before. And in fact, it is. It's actually divisible by 2 to the 6th. So we gain an extra power of 2. And Israel, in fact, proved that the number is actually exactly 3,264 divided by 2 to the 6th for the number of plane conics tangent to 5 general plane conics in characteristic 2. And we kind of have a sort of intuitive argument that justifies, so the 2 to the 5th is pretty clear. The extra power of 2, you can still try to justify thinking about configurations of dual conics and how that sort of splits up your count into halves. But we haven't really done it, so we don't really know. Similarly, another application would be de Jonquière's formula, which counts hyperplanes with prescribed computant multiplicity with a given curve. This is similar to the computation of theta hyperplanes that I talked about before. And so our point of view gives divisibility properties for the numbers of such hyperplanes, depending on the multiplicities and whether prime divides or not those multiplicities. I had prepared a little bit of something on Gromov-Witten invariants. I'm just going to flash the page, but I'm going to stop now because I see I ran out of time. So if you're curious about what this formula, what is the Gromov-Witten application, this is what it is. I'm just going to flick to the last one to thank you all for your attention.
Damiano.
So I'm going to switch back in case someone is interested in it. But are there any questions? Or sorry, I took over the stage. Do you usually ask for questions at the end of the talk?
I have a few questions. So I guess they're all sort of naive questions, but looks like Cecilia also has a question. But so, for example, if I understand correctly, in each instance you have sort of an enumerative problem that can be formulated in terms of linear series on curves, but in order to sort of detect what the resonating characteristic is, you need to do this additional thing of forming an incidence correspondence or calculating a Gauss map or something.
Yes, so in all the situations that we've seen, it was always contact multiplicities implicit in the enumerative problem that played the role. So it was either that you were counting inflection lines or conics tangent to given other conics, or bitangent lines. There was always an implicit multiplicity of intersection hiding, or maybe not even hiding, just very explicitly in your face. But there was this intersection multiplicity that was the thing that was creating the difference.
Right, and I mean, these are all instances where, I mean, over C, you would just be using Porteous or de Jonquière in general to calculate the degree of this contact locus.
Exactly. The point of view, though, is that when you use, for instance, de Jonquière's formula here, you're counting numbers in some way, not realizing the fact that they have accumulated somehow, because over the complex numbers, they have not accumulated.
Right, so that's why you have to form this incidence correspondence, right? So you see, I mean, you see this inseparability phenomenon happening at the level of a Gauss map or something.
Exactly. I mean, as we all know, multiplicities in algebraic geometry are very difficult to break. You do not expect that when you take a limit and when you specialize, your multiplicities decrease. And indeed, they do not decrease in this case either. They just condensate. So instead of having distinct points, your points collide and form lumps, all of the same size, all of size, well, multiple or power p or p, and then you count what's left after the fact. So you see how many lumps there are, and then you know that each one counts for p.
Okay, and do you know,
change?
Do you know of instances where, I mean, are there reasons to believe that there are sort of distinguished characteristics other than 2 and 3? I mean, I'm guessing that there are, but.
So, I mean, the computation that I talked about for multiplicities of roots works for any prime p. So if I go back to the slide here, for instance, this works for any prime p. The good thing about characteristics 2 and 3, the specialty about 2 and 3 is that when you're looking, for instance, at plane curves, you know that general plane curves have bitangent lines and inflection lines. They usually, in fact, general plane curves do not have higher multiplicity on tangent lines. So you would have to immediately restrict your attention to the special locus of plane curves that admit a point of multiplicity, a point whose tangent line is multiplicity at least 4, and then or maybe 5 to see a new prime. And then in that space, it might be that then 5 would play a role, but then you have to be a little bit more careful because you're not, I mean, you have to understand what the space of curves with a 5-fold intersection point look like.
I see. So
that's a problem. So we didn't think about that very hard. We imagine a similar story goes around, but we haven't actually worked out in detail whether that would actually work or not.
And there's no uniform procedure in general for predicting the tropical multiplicities.
Not that I know of. Of course, once you see this, you start realizing that in fact there might be. So in this case, there was only one special characteristic. But of course, you might be interested in looking at a line that is tangent with multiplicity 2 at one point and tangent with multiplicity 3 at another point. In that case, we expect the tropical count to be a sixth of the real count, of the complex count. But in characteristic 2, you would only get a factor of 2, and in characteristic 3, you would only get a factor of 3. So tropical geometry is actually going beyond a single characteristic. It's sort of taking the limit over all of them, and maybe even more, who knows. But in the specific cases that we looked at, there was only one characteristic that was sort of staring you in the face, and we just could exploit it.
I see. So I'll let Cecilia and then I guess Israel ask questions.
Yeah.
Hi, Damiano.
Hi, Cecilia. How are you?
Good. Very nice. Yeah. So I have one question. It's about the 7 bitangent lines. Do they give you 7 points that you blow up to get a dp2 tropically? I mean, could you see it like that? These 7 bitangent lines give you some kind of a choice of 7 points in the plane? that you can blow up?
Yes, in fact, the configuration of these 7 points is very special. It might be a little disappointing in that the configuration is always the same. So at least over not directly enclosed field, the configuration is always the configuration of the final plane. So it's always up to conjugation. It's always the sort of coordinate points on P2 of F2. Sorry, not the coordinate, all the points on P2 of F2. So it's actually, when you blow it up, it's not on the theta surface because many of those lines, many of those points are collinear. Sorry, many triples of those points are collinear. But it is a very interesting surface. I don't know, so people haven't really studied the sort of the arithmetic side of that. So I said they're all conjugate, just like diagonal equations are all conjugate to one another. That doesn't prevent people from looking at diagonal equations and studying them arithmetically. So I don't know if people have studied the sort of twists of Fano planes, but that would be what it is. Here, I mean, you probably know, you can probably say that the Galois group that is relevant in that case is PGL2, right? So PGL3, and I mean, it's beautiful, and you can probably do a lot of stuff with it.
But then to get a tropical DP2, also you don't take like a degree 2 map branched in a like degree 4, like, because then you get only 14 lines on the surface from the count. How do you do that?
I don't know about constructing tropical theta surfaces, so that I don't know.
Because the tropical DP3s, I think that's what is known so far until now, and they are shown to have exactly, I think, 27 lines if you count them well, properly, right? Yes. So the 7, actually there is like an infinite number, right? And the 7 that you have is like classes of lines from what I knew. This paper of Matt Baker and many others, they show that you have 7 sets of lines.
Yes,
not 7 lines, right?
Similar to the situation with inflection lines. So you have connected components of the space of the set of bitangent lines in that case as well. And you can have 7, 4, 2, or 1, which is also the numbers of bitangent lines that a plane quartic over F2 can have. You can only have 7, 4, 2, or 1 bitangent lines. You cannot have any other number. And again, in the tropical world, they're besides being counted with multiplicities, they're also counted with connected components. So
no tropical, like DP2 from this.
I don't know. I haven't thought about that, so I'm not really sure. The configuration of 7 points is very special, and you can say what it is. How that relates to tropical. In fact, I'm not sure what the configuration of the 7 tropical is either, precisely because it's these sort of connected.
And the thing is that it is very hard, I think, like tropically, to get 7 points in GP, like that you don't have 3 on the same line, 6 on a conic. At least I've been trying to do this, and like normally they are not, they fall in the same line or they fall somewhere. There's always some kind of curve that gets them when you go to 7. When you go to 6, you do.
So it might then be a reflection of the fact that the configuration of those 7 bitangent lines in characteristic 2 is the final plane. So you're actually guaranteed that there are triples of points that are collinear.
Okay, thanks. Yeah, great. Thank you.
You're welcome.
So either Israel or George, I think, has a question.
So Israel, do you want to go first? Okay, so I'm trying to
give my question, so I didn't think I had to talk.
So let me try to fetch the question. I guess it's here. Okay, so the question is there a tropical count for either 3,264 or 51? I don't know. So you're referring to Steiner's conic problem. I don't know. If I were to guess, so I think maybe the answer is no. If I were to guess, my guess is that the tropical count would tell you either 51 or at best 102. More leaning towards a 51, but I really do not know. It would be, in fact, I think you can probably prove that it has to be at most 51 because the tropical count would have to factor, and then there's your result about the fact that there's only 51 in characteristic 2. I'm guessing that presumably 3 and 17 do not cause problems because there aren't multiplicities 3 or 17 that appear from 5 general plane conics and conic tangent to all of them. So I suspect the tropical count would be 51, but I do not know, and I do not think it has been done.
Yeah, I don't think that's known.
Okay, so do you hear me?
Yes, I can. Yeah.
Good. So I'm trying to reconcile your talk with another talk we listened in the seminar a few months ago. So Josué Moratori recalled us a node result of Darboux that says that for a general surface on P3, there are exactly 27 conics with tangency of order 7 at a given point. And I'm kind of puzzled because 7 does not divide 27. So I don't know if you... I don't...
Can you I'm going to take note of the numbers so that I can keep them in my mind. You said for a surface, a cubic surface or general surface?
General surface. General surface, degree at least 4.
Degree at least 4 in P3?
P3.
Yeah.
So you have 7 exceptional, and you fix a general point, and so you have 7 exceptional conics, or you have 27 exceptional conics, which will intersect your surface at that point with multiplicity 7.
So these are not conics that are contained in the surface.
No, they are outside the surface. So this is a node result of Darboux that Josué Muratori recovered and generalized to arbitrary rational curves. I remember his talk correctly.
So the situation seems a little bit different because we were explicitly using the fact that we could reconstruct the coordinates of the intersection point because because we were using the equation of the curve. So here you have the equation of the surface. I mean, I completely agree that there aren't lots of divisibility properties in this problem. So I wonder whether, so I think maybe, I mean, it might be interesting to see whether modulo 7, something special happens. Maybe modulo 7, these 7 conics become only 1. But it seems to me that it's a little different from...
certainly different, you're right.
It would still be a fun question to see whether characteristic 7 plays a special role in this problem, but I do not think that it follows, at least I don't see how it follows in the framework that we're saying. Even so, whereas the 51 that Israel computed seems to be close at hand, what you say, I would be a little bit more skeptical.
Okay, thanks. Yeah, I clarified a lot.
So any more questions for so if not, let's thank you again for his talk. And all of you